Hello students, today we are going to start new chapter, Oscillations. This is the 5th chapter in our syllabus. You know oscillatory motion and examples of oscillatory motion. Just we revise the examples here of oscillatory motion. So the first example we take here, swinging a swing. You have enjoyed swinging on a swing. The second example, motion of a pendulum. This also you have observed so many times. Third one is also the example in our day-to-day life. It is the motion of needle in sewing machine. We first take the example of motion of pendulum. If here with a light string, inextensible string, a bob is fixed here. If this string is displaced from the original position, here original position is suppose denoted by O. If it is displaced, this bob is displaced at position A through this path, and angle made by the string with original position is theta. If it is released from A, it moves again towards the mean position or original position, then it goes towards the left position like this. That position is denoted by P. From this also it again comes to original position. This original position is called as mean position. The rightmost position is called as right extreme position. It is also called as right extremity. This A is called. B is called as left extreme position. Also it is called as left extremity. And about the mean position, that is usually called as equilibrium position. You have to know all such terms which are related to the positions. So about this mean position O, bob of simple pendulum moves to and fro. This motion is to and fro motion of the bob of a pendulum. Mean position to right extreme position, mean again from right extreme position to mean to left extreme position, and again to mean position. Here there is a set of movements. We can write like this. Pendulum bob starts from O to A, then A to O, O to again B, and from B to O. Then this set of movements is called as one oscillation. It is called as one vibration. And this set of movements repeats in equal intervals of time. Therefore, this oscillatory motion is also can be taken as the example of periodic motion, because you know periodic motion is the motion which repeats itself after equal intervals of time. So oscillatory motion is one of the examples of periodic motion. Already in rotational dynamics we have studied uniform circular motion is also a type of periodic motion. So here oscillatory motion is a type of periodic motion, and one oscillation can be given by one such a set of movements in this example, and it is applicable for all such examples. So here we take again one example, that is motion of needle in a sewing machine. If we show the needle here in this position, this position is original position, it can be a mean position or equilibrium position. When it goes up, its position is denoted by A. It is called as upper extreme position or upper extremity. When it comes to O, again it moves to B, that is called as lower extremity. So here the set of movements is up and down motion about a point O or about the mean position. In this case it is up and down. In case of pendulum it is to and fro, but it is also called as a oscillatory motion. Oscillatory motion can be the motion which takes place or which occurs along a certain fixed path about the mean position or equilibrium position, and such examples we have to study in this chapter. So here we take one example of oscillatory motion. That example is of spring mass oscillator. In that example we have to study Newton as well as the simple experiment. Here I draw one setup like this. Suppose here there is a rigid support and one horizontal surface is set here, that is frictionless horizontal surface. On that, here spring is attached to a block. Here this is a block. To the block spring is attached. This block is having mass m. This is a spring, and this spring is not acted upon by any force. Force on the spring is 0. Force exerted by the spring is 0, or applied force is also equal to 0. In this case we can say that spring is relaxed. It is not under certain tension, therefore we say relaxed spring. Now on the same setup, if we show the same setup here, but the spring is stretched so that the block is at this position, and the spring can be shown, stretched spring can be shown like this. Here we can say that spring is stretched and it is towards the right. Here automatically this block displaces through a distance x. The displacement of the block, say it is the original position, this is the original position here, the new position the block has taken, it is A, suppose it is denoted by A. Then as soon as we stretch it, block is at position A. Now in the next step of the experiment, here block is released. Then block moves towards O, but it does not stop here. It moves towards the left, so that the new position of the block can be shown in this way here. This is the new position. The same situation we have to show here. Surface is same setup is there, but the block takes its new position at B and the spring is compressed here like this. Block is same. It goes from the O position, or from O its displacement can be shown by X. Towards right its displacement is X. Towards left also its displacement is X here. And for some time interval we observe the motion of block in this way. Original position A, at position A, when it is at right extremity, at B can be shown like this. So this is to and fro motion of block. To and fro motion of the block along the line which is AB line, and its mean position is O. A is right extremity, B is left extremity, you know it is, and this O is mean position. So this experiment can be repeated here by considering again the block at O. If it is stretched to A and released, then it performs the oscillatory motion from O to A to O, O to again B, B to O, like this. If it is repeated by compressing the spring, if instead of stretching, if it is compressed and then released from this, then also it performs the oscillatory motion. But we have considered such motion here by stretching the spring. So when the spring is stretched, this position, this figure is denoted by figure A. When the spring is relaxed originally, that figure is figure B, and the compressed spring can be shown by figure C. Here we have shown the positions only, but the motion is continuous. It is to and fro motion of the block along the frictionless surface, along a straight path on the frictionless surface. Therefore, this motion can be taken as the oscillatory motion of this mass oscillator or block oscillator. And set of moment is from, you know, it is from O to A to O, O to B, B to O, like this. Now, here what we have to consider its cause, why the oscillation occurs here. If we show the block at position O and then spring is stretched, block moves at A, we know its displacement is X from the mean position here. But what actually happens in the spring? The spring is elastic. Here there is restoring force sets up in the spring. That restoring force can be denoted by F. And as we displace this block from O to A, and it increases when the displacement increases. So restoring force increases with the displacement, but its direction is opposite to that of the displacement. restoring force can be shown by this arrow. Displacement is from O to A, but direction of force is from A to O, or opposite to the displacement. Here we can write the expression for it as F is equal to minus Kx. Avoiding this proportionality sign, K is constant of proportionality, but it is called as force constant. It can be given as K is equal to minus F upon X. By magnitude it is F upon X. It can be defined as force per unit displacement. Now the same is the case here when this block moves from A to O. It does not stop here because kinetic energy becomes maximum at this O and it moves towards left. In this case, in this system, the spring gets compressed. Again here, by on account of its elastic properties, restoring force sets up in the spring, but the force is towards the mean position. Force here can be shown as towards the mean position. It is again equal to F is equal to minus Kx. In this case also, restoring force F is equal to minus Kx. But in the mean position, F is equal to 0. So in both the cases, F is directly proportional to X. Restoring force is having opposite direction to the displacement, and it can be written as K is equal to F upon X by magnitude. So by magnitude it can be F upon X. It can be defined as force per unit displacement. Now here, as the motion is to and fro motion for this spring mass oscillator, this oscillatory motion is simple to describe. Therefore, and this as oscillatory motion can be explained by using the sine function, harmonic function. Therefore, it is called as simple harmonic motion. Simple harmonic motion. So just I repeat here that for the case of simple pendulum, needle, motion of needle in swing machine, in case of spring mass oscillator, even if we have described such description that is force is directly proportional to X and oppositely directed, here this such types of oscillatory motions can be explained by using the trigonometric relation ratio like sine ratio or cos ratio. These motions are harmonic motion, sinusoidal motions. The oscillatory motion, which is simple to explain or simple to describe by only one function, can be called as a harmonic motion, and here it is simple harmonic motion. As it occurs along a straight line path like this from O to A, O to B, such path that we have shown in another diagram like this. The path of motion is straight path. This motion can be called as linear simple harmonic motion. Sometimes the path is arc of a circle like this. Suppose we have such long object here, and if this object is rotated along a curved path or arc of a circle, the path is curved here. It can be shown like this. Suppose originally this object is like this plane like this, and if it is rotated in this way, then the path of oscillation is curved, in that case the motion is called as angular simple harmonic motion. So both these types of motion we have to study in this chapter, oscillations, and in detail we have to study these motions. We have started the discussion from the oscillatory motion, which occurs along a straight path, means it is linear simple harmonic motion. So first we deal with linear simple harmonic motion by considering the equation that gives the relationship between force and displacement from the mean position. So here angular simple harmonic motion is the last part or last but second part of this chapter, and the first part of this chapter is linear simple harmonic motion. So we have to define it. So from the explanation we can take the definition of linear simple harmonic motion. It is again from the same explanation. Linear simple harmonic motion can be defined as to and fro motion along the straight path about the mean position, some mean position, in which the force is directly proportional to displacement from the mean position and directed opposite to the displacement. Such simple definition we can take for the linear simple harmonic motion. Now the next point here is the equation which can describe the linear simple harmonic motion is the differential equation of linear simple harmonic motion. It can be abbreviated as linear simple harmonic motion. So for that we take the same relation that F is equal to minus kx. Here according to Newton's second law of motion we have one more relation, that is F is equal to ma, where a is the mass of the block or mass of the object, a is the acceleration when it moves from O to A or A to O, like this. If we have such relations we can equate the relation ma can be equal to minus kx. So this is first equation, this one is second, this one is third equation. Now we have to substitute for a. We know definition of acceleration. A means acceleration can be defined as rate of change of velocity. In terms of derivative it can be like this, a is equal to dv by dt, and also we know v, velocity, is the rate of change of displacement, means dx by dt. If we substitute this velocity in acceleration, a is equal to d dt of dx by dt, it can be equal to d square x by dt square, d square x by dt square. A is equal to, means acceleration can be written like this. Here if we substitute acceleration in this equation 3, so consider equation 3, ma is equal to minus kx, m into d square x by dt square is equal to minus kx. We can write d square x by dt square is equal to minus k upon m into x. Also we can write it as d square x by dt square plus k upon m into x, it is equal to 0. This is our fourth equation. Here we introduce one more constant in this equation, d square x by dt square plus, here we substitute for k upon m can be substituted as omega square, where omega is angular velocity or angular frequency. Here k upon m is equal to omega square. Now substituting that, we get d square x by dt square plus omega square x is equal to 0. This is the fifth equation. So equation 4 and equation 5 gives us the differential, here differential equation of linear S.H.M. It involves derivative of x 2 times. It is called as differential equation of S.H.M. Now the new quantity here, omega square, actually we have taken this quantity in uniform circular motion. Omega is angular velocity. This quantity we have introduced here, but the reason we will study in the next point of this chapter. That point is like this: S.H.M is the projection of UCM on any diameter. Here S.H.M and UCM are related to each other. Mathematically, we have to show S.H.M is the projection of UCM on any diameter. Then we relate the term omega. K upon m we have taken as omega square. So here there is relationship between S.H.M and UCM. Therefore we have taken that term. But at this stage you remember that term, and we will understand that term when we take this point. Actually in this syllabus this point is deleted. Still we have to consider that point and then we will go further. So here in today's lecture we stop here. After completing this differential equation of S.H.M, and in the next lecture we use this differential equation to have the relationship of displacement from the mean position, velocity of the body in simple harmonic motion, acceleration of the body in simple harmonic motion, and then we study this relationship between S.H.M and UCM. So today we stop here. Thank you.